Here we have Guest of Honor Academic Series. It's a dual webinar with Professor Ruslan Salakhutdinov. Professor Ruslan Salakhutdinov is a professor of computer science at Carnegie Mellon University and also ex-president of research at Meta and ex-director of AI research at Apple. Professor Salakhutdinov research spans in deep learning, probabilistic graphic models, multimodal learning, generative AI, and large-scale optimization. He completed his PhD at the University of Toronto under Geoffrey Hinton, widely known as Godfather of AI, and awarded of 2024 the Nobel Prize in Physics. Through his leadership roles in both academia and industry, he has contributed significantly to modern advances in generative model, multimodal AI system, and autonomous AI agents. So during today's session, Professor Salakhutdinov will share insight on the future of the autonomous AI agents and multimodal intelligence, the role of cutting-edge AI transforming science, industry, and society, and how emerging regions can participate in it and contribute in this rapidly evolving landscape. So, and he will also give some practical recommendation, maybe pathways with our audience today, PhDs, postdoc professors. So,
okay, excellent. So, my name is Ruslan Salakhutdinov. In the US, I go by Russ Salakhutdinov. I thought I'll give you a presentation about the work that we're doing and research a little bit about the past history and such for about 30 minutes or so. And then I would be happy to do a Q&A session. So just a little bit about myself. As was mentioned, I was born in Uzbekistan. I grew up in Tashkent. After I finished my high school, I went to the US and did my bachelor's at a small school in North Carolina. It's called High Point University. Once I finished my bachelor's, I got into PhD program, master's and then PhD program at the University of Toronto up in Canada, where I was doing my PhD in generative modeling and machine learning in general with Geoff Hinton. Then I spent a couple of years at MIT as a postdoc working with a professor called Josh Tenenbaum. And then I came back to Toronto as an assistant professor. And in 2016, I moved to Carnegie Mellon University, where I am right now as a professor. So this is sort of my academic path, and I'm still at Toronto, at CMU here in Pittsburgh, Pennsylvania. Just a little bit about my entrepreneurship route. I'm happy to answer questions about this as well. Back in the day when I was at Toronto, I co-founded a startup called Perception Machines with a couple of my students. We worked on deep learning for computer vision, for autonomy. And then we started collaborating with Apple, and then essentially Apple acquired our company. We've talked to Tim Cook, and the decision was made for us to go and actually do the work at Apple. And this is how I ended up at Apple, was the director of AI research, working on different areas, primarily on self-driving cars, computer vision, and then eventually moved into health and Siri. And then, after some time at Apple, I came back to CMU. What's interesting is that a few years ago, my lab started working on a genetic model, some of which I'm going to discuss today. These are digital systems, digital agents that can go do interesting things for you. And then the research that we've done at CMU, we had a huge interest from industry. We actually went to Seattle, talked to the Microsoft team. Satya Nadella, the CEO of Microsoft, was very interested. And at the same time, we actually ended up going to Silicon Valley, talking to Mark Zuckerberg, the team here at CMU. And then the decision was made for us to go and do our research at Meta. And this is how I ended up at Meta, essentially doing research on agentic system, reasoning in agentic systems. And I've left Meta a few months ago, and together with a couple of friends, we co-founded a startup called Sooth Labs, where I am a chief science officer. And the startup sort of focuses on what we call forecasting engines or forecasting systems, using existing AIs to make long-term forecasts. It's an interesting experience because all my previous startups were basically building the technology and then essentially exiting to the big companies. This one is actually trying to build the actual company. We've just raised, I think, 55 million seed round. which sort of allows us to start building these models. Okay. Now, let me kind of talk a little bit about like where AI is going. I'm sure many of you are aware that, AI has been, especially over the last few years, been, exponential growth in the capability of these models, looking at vision systems, recognition systems. Reasoning is an interesting area. Language understanding, we see chatbots and agentic systems, as well as robotics. There is sort of, over the last year specifically, I'll show some examples, been a lot of interest in robotic systems. And what's really driving a lot of the progress is obviously machine learning. So these are models like transformer-based architectures. But most importantly, also the data becomes very important asset, as well as the infrastructure for building and training these models. So if you look at perception, you look at conversational agents, recommendation systems. Also, a lot of interesting work is happening in medical space, medical analysis, lots of advances of AI in that space. And obviously, there's been a lot of robotics now, home robotics and self-driving cars. And right now here in Pittsburgh and in California as well, you have Waymo that's actually like drives without a driver. I had a good experience driving Waymo without a driver. It was a very weird experience. You sit in the car, there's no one in front, and the car just drives. But the drive is actually pretty good. Now, a lot of, generative AI, what's been happening in generative AI? Obviously, is a huge progress in natural language understanding, conversational AI, and agentic AI. And I'll focus in this talk a little bit more on agentic AI. We start seeing superhuman computer vision, image video generation models. We see examples of large-scale self-supervising, multimodal learning. Huge commercial investments in AI and machine learning, especially here in the US. It's, the investments especially in the startup space, in companies, is just astronomical. As I've mentioned before, people are getting seed rounds. Seed round basically means that you kind of like have an idea of what you want to do, but you don't have a proof sort of record of it. You get on the orders like tens of millions of dollars, sometimes hundreds of millions of dollars that go into AI startup ecosystems. So LLMs, agentic systems, as well as robotics, perception space. We see lots of applications of AI for public health, AI for drug discovery, lots of startups in that space. I'm being an advisor for a couple of them, especially in the space of AI for drug discovery. Very, very interesting area, building foundation models for biology, AI for environmental sustainability, and also privacy. That's sort of one big area of research. Now, let me show you a little bit of how we've seen the progress, right? I show this slide because, back in 2014, when we were building generative models, when we were generating faces, this is what the state of the art looked like. And just over the next 4 or 5 years, we went from generative models being sort of very weak to being really good. And the progress in generative modeling over the last, 5 to 6 years has been, phenomenal. Here's an example. I like this example because it's sort of one of the early examples of conditional generation, where from horses, you can translate horses into zebras. And a lot of ideas of machine translations, just like you translate, English to French, you translate one image to another image. And people have looked at things like style transfer earlier in a day, and so it's sort of been big progress. One interesting things that we see today is this notion of reusability of large-scale pre-trained models. Right, it all of it started back in 2017 when one of the early models called ResNet was developed by Microsoft, and people started adapting it for all kinds of problems. So, for example, this was one paper that showed that if you take ResNet model that was trained on images of natural scenes, like these types of images, right, that you're seeing here, can be adapted to detecting skin lesion. Which is one of the early sort of examples where people say, well, how can you train a model on just natural images, forests, people, iPhones, table, desks, whatever, just at very large scale, And how can you adapt it to, detecting skin lesions, right? So it's like detecting, transferring it to very niche medical application, and the systems would work remarkably well. And that now goes into the setting where a lot of frontier labs, anyone who releases open source models, a lot of times you'd release a base model and people would fine tune them for specific applications. So obviously we see examples of OpenAI, Anthropic, anything from question answering systems, retrieval, code generation, agentic systems for code generation. And of course, one of the things that my lab, I also emphasize a couple of things that my lab is working on really two sort of directions, but very combined together. One is the physical AI. So we see a lot of systems that we see today, like Anthropic or OpenAI or Gemini. We think of them as digital agents, right? The digital systems. You can talk to them, you can get the information from them. In parallel, there is a lot of development on what's called physical AI, meaning AI or robotic systems that can actually, or AI systems that can interact in the real world, in the physical world. So for example, you have an agent can take actions, receive observations, states from the environments, and then get the reward. And obviously to build physical systems, you need to be able to move around autonomously, localize, plan, multimodal input, understanding human speech, reasoning, and so forth. So when we think about physical intelligence, think about agentic system. Then the agentic system takes an action. Let's say you observe something in the environment, and then you take an action. Here's an example of what's called the navigation system. So this is a visual navigation system. At this point, that area is fairly close to actually being solved. But obviously, agents need to move around the world physically and require some spatial and semantic understanding of 3D environment. Here's an example. This is an example that was built here at CMU. You're trying to find a potted plant, and there's a little robot that moves around. It builds what's called semantic map. So it builds the environment of the obstacles, the objects around, so that you can figure out how to navigate in that space. And you can see this little robot. This was an early work that was done. You can see this little robot, and the full vision stack is running on this robot, so it can takes actions, how to turn left, how to turn right, and sort of move around in that space. And what it's actually doing is building this 3D, what we call 3D semantic mapping. As it moves around in the environment, it starts building, what the environment looks like. This is called simultaneous localization and mapping. And also identifying objects around around the environment. So that imagine at some point there's a lot of work where you have a robot. The robot sort of comes to your home, moves around, navigates, and figures out what it needs to be, what it needs to do in your home. So these technologies are getting much more mature at this point, to the point where this problem is actually fairly close to being solved, which is remarkable. Of course, deploying robots in households, like in apartments and such, is still very, very challenging. And again, this was done in my student's home, and this is the robot that moves around in his home and navigating and mapping the environment, which is pretty exciting. One of the other areas that there's a lot of research is on what's models called visual language models, or VLMs, where you're combining vision aspects. So this is what the agent sees environment, plus the language. So for example, I can give you an instruction of what the agent needs to do. So for example, I can say, drop a clean pen on the table. And so there is a language part that comes in. There is a semantic search, which tries to identify what environment do I build, what semantic map do I build, and then it goes to actually taking actions, low-level actions. How do I move 30 centimeters forward? Do I rotate left? Do I rotate right? Right. So these models, and there is like extension of these models called visual language action models, because you're actually trying to take a low-level actions in these robotic systems. And this is what it looks like. This is a simulation environment, right? You sort of ask the instruction, the agent goes and completes sub-goals and builds the environment fully autonomously, right? And the reason why it's called following instructions, because you need to be able to build systems that understand the instruction, have a good language understanding of the instruction, and follow and execute those instructions. Much like in the frontier labs, people are fine-tuning models to do instruction following. You can do the same thing for physical agents. And one of the very sort of exciting areas that people are working on right now is extending these visual language models or visual language action models into manipulation, right? And so here's an example of, so let me just go back for a second. Here's an example of the robot trying, to assemble, task is all done and like not very successfully, right? And so these are settings where you're training the robots to actually manipulate objects, which is one of the core areas of robotics that we see today. And just to emphasize, hundreds of millions of dollars go into the startups, go into the frontier labs to build systems that can manipulate objects. Here's an example that we've built here at CMU. I can give an example, put the mouse in the drawer. Success rate is about 90%, obviously not good enough for the real systems, but you can sort of see systems, maybe you're going to have a robot that can cook a meal for you, right? And so placing objects in the pot and then moving things around. Obviously, this is mostly manipulation task, and then generalizing to new novel objects, geometries, and such. So lots and lots of interesting work happening there. I think some of the challenges is building the hardware and the ability to manipulate fine grain objects or small objects. Still quite challenging, but you can imagine in the future you're going to have systems that can, for example, cook the meal for you, right? This is still early, so it's going to take a little bit of time, but the progress has been quite strong, at least over the last 5 years. Okay. And of course, one of the things that people are now looking at is building foundation models that incorporate many, many modalities, not just images and language and audio, but looking at the sensors, looking at time series, looking at sets, looking at all kinds of pieces that can go together and build a foundation model that can do a lot of different tasks. There's a lot of work that's happening. One of my former students, who's a professor at MIT right now, Paul Leering, is essentially focusing on building these kinds of models. Okay, and it's sort of, all of this is building towards physical agents, right? Physical agents that can manipulate objects and do it in the real world. Now, over the next, 15 minutes, I also wanted to talk about digital agents. So digital agents, you can think of them as the same as physical agents, but that operate in a digital space, right? And this is where large language models, I'm sure many of you have heard about large language models. The ability of these models has been spectacular, right? You have zero-shot ability. You have something called in-context learning. These models have world knowledge. They can generate long and coherent text. They're sensitive to word ordering. And so there's a lot of representation learning that's happening with these large language models. And what we see today, where the technology is moving towards, is building what we call autonomous AI agents. So, and a lot of tasks that you can perform today in a computer will be automated going forward. And a lot of these tasks, tasks that you're doing on the web, there's lots of opportunities to automate these sort of menial tasks, tasks that humans would not want to do, and also augment human capabilities. And for the rest of the talk, I'll focus a little bit more on web kind of tasks, so what we call computer use agentic tasks. So models that can actually control your computer and solve, do tasks that you can do on your computer. So it brings me to the notion of web agents. And you can think of web agents as, one concrete way is that the agent, the AI, sees your screenshot. It also has certain elements associated with the screenshot. That's the observation, right? The observations goes to the agent. The user gives the query what you need to do. The agent does some thinking or reasoning, and then takes the action. on the web, and once you take an action, actions of the form like clicking, typing, scrolling, whatever a user would do, whatever you would do on your computer, the agent can basically do the same set of actions, and then it gets into observation. So if you look at this system, agentic system, it's very much similar to what we've seen in the physical systems, right? The agent observes the environment, it takes an action, and then it gets the reward, whether this action was good or bad, and then it takes and then it gets the next observation. So Web Voyager was one of the early papers that showed this example. There is another settings called Online Mind to Web. Again, very much the same sort of setting, but done a little bit better, where you have an agentic system that takes screenshots, and you have more sort of concrete tasks. So for example, one of the tasks could be look at the news refrigerator that's 34 to 36 inches wide. I want it to be priced between $1,000 and $2,000 and has a customer review rating of 4 stars or higher. So your agent would go online and try to accomplish this task on your behalf. Okay. One of the things that we've been looking at recently, and this is the work that that got inspired after we did the work at Meta, because we realized that a lot of agentic systems that we have today actually fail on what we call long horizon tasks. So think about agentic systems that can spend hours trying to solve the task. In the future, we're going to have agentic systems that will spend days solving the task autonomously, right? And we've tried to kind of build those types of environments, and that also thinking, how can we build what we call multi-agent systems or multi-agent environments. And Odysseys is something that we've built here. We've actually collected data from people. So we've tried to identify how people are using the computer. So for example, you want to plan a trim to Palm Spring wedding, you want to search the flights, you want to find the drive time, you want to book the hotel, you want to rent the car, you want to assess like other interesting detours you want to make on your way back, and then you want to build the itinerary, right? And so it sort of requires a very long planning process. And one of the challenges of building these types of systems is evaluation. How do you evaluate whether the system successfully completed the task or not? So in things like math, for example, I'm sure you've seen a lot of examples where AI for math, where AI can solve complex math problems. A lot of these systems are trained on what's called outcome-based reward, meaning that you give it the problem, math problem, the model thinks and gives you the answer. It gives you the answer, and the answer is always either right or wrong. There is no sort of partial kind of correct answer. And you can train these models to actually produce the correct answer. Here, for these kinds of tasks, especially if that requires, humans to, do these, there are many different ways of solving the task. There's no one concrete correct outcome. And so this is where we've built what we call rubric-based evaluation. And the rubric-based evaluation essentially looks at sub-trajectories of the task and says, well, have you actually looked at the flights? Have you figured out what the drive time should be? Have you looked at the rentals? And so as long as you're sort of doing a lot of these things that I'm asking you to do, then I can identify you as being correct. So here's one of the tasks, which is the task that was designed by students here at CMU. It's a long task. Just to show you, a lot of times when PhD students or like master students or bachelor students want to apply for PhDs, you can give it a task of saying, well, I want to apply for computer science PhD programs in machine learning and AI. I want to look at the top 25 US computer science programs. I want, give me an Excel spreadsheet with programs and advisors. Go through these different professors, see who is hiring PhD students. Are they accepting PhD students? Give me the exact wording, what they're looking for, and then for each promising professor, or actually give me the link to the web page. I want to look at, are they accepting the PhD students? Please record at least 20 professors and try to look at different professors across, schools, not just MIT, Stanford, Berkeley, at CMU. I want broad application strategy. And so this is fairly involved task, right? Even as a human, when you're trying to solve these tasks, it's very difficult. And we have many examples of this where, you're trying to look for a right surgeon for your procedure. You're trying to look for postdoc or for faculty position, or there's a lot of different things that you can ask the computer to do, and you can sort of see it's fairly challenging task. And here's what Claude Opus 4.6 was doing, right? And this is just to show you what existing systems can do. It goes on the web, it sort of looks at the computer science rankings, it goes, creates the Excel spreadsheet. This is all done fully autonomously, which is actually very remarkable. It goes through faculty, some of these faculty I know. It sort of like tries to go through different schools and looks for PhD programs, looks who's looking for PhD, who's looking for students, and areas. And so you can, a lot of professors that it's looking at, I'm actually able to identify. This is sort of an example where it solves, but it doesn't fully solve the task. So this would be almost a task that solved partially, right? And so, and these are rubrics that you can decide to evaluate how good the model's done, right? Has it looked at, the 25 top US schools? Has it looked at the faculty directories? Has it looked at the personal web pages and so forth? And what we see is that a lot of frontier models are solving tasks, what we call perfect, meaning that, has it actually completed all the rubrics-based judges? So has it actually successfully solved the task? About 53% of the task is actually doing, which is actually very strong, because we don't think humans will get to that level either. So machines right now, some of these long horizon tasks, I think they are on par with humans or can do better than humans. What's interesting is that you can see the difficulty for easy tasks. Frontier models are at almost 100%. So simple things existing models can do. Hard tasks that require you to actually do reasoning and thinking and search for a lot of different details, models cannot do. But this would also be very hard for humans as well. I spent, when I was applying for postdoc positions, I think I've spent at least a week looking for who is looking, who is hiring, who is, and so as you can imagine, those kinds of things are going to be replaced by computers. And obviously, as the step budget, how many steps, how many actions the agent takes, models typically tend to plateau around 100 steps, but even the best models sort of take more than 30 minutes at this point, and they become very expensive. One of the interesting things that we found is that on the failure analysis is that Opus, for example, this is Claude model, Anthropic's model, it sort of tries to overinvest in research and tries to gather information without actually producing the final outcome. So it does a lot of research, but doesn't produce the outcome. GPT fails through inaction. So it generates the report and sort of plans, but then it fails to actually execute. For long horizon tasks, both models tend to stall in early stages, right? So one of the issues is that things that require very long again, these are very long horizon tasks that requires for example, I want to visit like 30 different restaurants. So I want to visit 30 different universities. Then these models tend to get stalled in gathering information and sort of trying to basically failing. So it's reasoning. On the other hand, we found very interesting capabilities. So for example, GPT, when it looks at broken web pages, it tries to extract structured data and metadata. So when you see when the web page is broken, you can't see it. It's trying to actually look at HTML and try to get from the source and tries to extract information behind the source. Opus shows complementary stacks. What it does, it tries to bypass access issues. For example, you have 403 error. It tries to go to archive with a Wayback Machine and tries to retrieve the data from the archive, right? So for example, you can recover class schedule information that would not be available through direct browsing. And this also, interestingly enough, raises issues such as safety, right? I go to the web page, I have 403 error, I can't see it. Any reasonable human would say, okay, the information doesn't exist. Frontier models are trying to kind of almost try to bypass this. They either try to look at raw HTML or they try to look at the archive data. They still trying to figure out, can they get the information? This is something that interesting enough because, for safety sort of critical applications, these models will try to go around, right, and retrieve or try to get the information that otherwise would not be available. And the last part I want to briefly mention is the multi-agent settings. What I've talked about is agentic systems that can, they try, but a lot of times they would fail, right? Single agents, they sequential, they inefficient, they struggle on long horizon tasks. What you really need is you need systems that can decompose, you can parallelize, and you can replan. And this is what our first attempt at building these, what we call multi-agent computer use systems, where you give a user task. There is a manager, think of it as a frontier model, that initializes what we call a direct acyclic graph, a DAG, of what tasks you need to do. And in what order. So it does the reasoning, it does the planning, and then you instantiate multiple agentic systems. These could be small agents, and then they go and execute subtasks. And then the manager aggregates that information and decides whether you need to redo some tasks or whether the task is complete, and then you go to the next subtask. But the idea is that at the high level, you have a manager system that kind of coordinates these local agents. And these local agents, they go solve the tasks, they come back to you, and the manager can replan. Here's an example of where you have an attempt to go through GUI interface. I think here you're trying to do something to the image, like adjusting the brightness and adjusting the color, the background color. And the point here is that the agent goes through the GUI interface. It's trying to go through GIMP in this case, trying to switch. It fails. It goes through command line interface. It fails. It recovers. It launches recovery attempts, which is interesting enough because the manager says, look, I haven't solved this task. Try to recover. If you fail, try again. And then it revises a new strategy and another command line interface attempt, and then it solves the task successfully, right? So you imagine these systems where the agents would go, and if they fail, they'll try to attempt to solve the task again. And this is the beauty of the multi-agent systems, because you can have two parallel agents trying to solve the task. If one of them fails, the other might succeed. If they both fail, the manager can refine the strategy, refine the reasoning, and then go and try it again. And what we see is that across multiple different data sets, a lot of times, you have positive improvement in success, right? On Odysseys, these are probably the most challenging one. You have significant improvement in performance. And this is just to say that more effective test time scaling. So these systems, the multi-agent systems, can be much more effective in test time, meaning that they can spawn different sub-agents, try to solve the task, come back. If they can't, condition on this information, you spawn new sub-agents, and then they can solve the task. And so again, here, just wanted to show you that single agent versus multi-agent. And so anytime you have success of a single agent with multi-agent framework, you can actually do much better. And obviously, parallelization saves times. One interesting thing is that we've seen that agentic systems fail to do planning. This is one of the biggest issues, especially for tasks that require you many hours to solve. And we see that replanning here becomes critical. So what that means is that you have a manager system with sub-agents that can replan. It can significantly improve the accuracy. So for example, we see examples of something like MapReduce, parallel information gathering. So I'm trying to get some information. I can dispatch multiple agents to go gather this information, retry an exploration. If the agents fail, I can set another agent to go try to explore and then come back. And what's interesting is that we found, in terms of the key findings, is that these multi-agent systems, they achieve test time scaling through parallelism and multi-agent coordination. So running parallel and coordination. The strongest gains we saw comes from continuously replanning. So if the agent fails, it continuously replan and does the parallel execution of specialized sub-agents. Multi-agent coordination also, interestingly enough, enables recovery from failures. And that's important because a lot of previous systems, they would try something, they would fail, and then they would not know how to recover from the failures. These multi-agent systems have the ability, because you can parallelize and you can replan, to recover from failures. And this is something that we're beginning to see. It's very early in the research. And obviously the framework is agnostic and can integrate multiple agents. I also wanted to show that we've been building systems for agentic systems that can control your phone. We have built an environment where you have a particular user, Jordan, that has access to many different apps with synthetic data. And this is what the simulator, this is a fully simulator looks like, and this is what your personal iPhone would look like. So you have flights like Alaska Airlines, you have food, you have weather, you have clock, you have like version of Shopify when you can shop on things. So these are full kind of mimicking the iPhone ecosystem, but you can imagine systems, agentic systems that you can train using reinforcement learning. This is something you can book the flights. So you can basically have the ability of these models to run on your phone. One last thing I wanted to mention is that these are students, amazing students who are doing all the work. These are students in my lab. And just very briefly, I do want to mention some of the recent lab members. A lot of students from my lab actually go to the universities. Ben Eisenbach is now a professor at Princeton. Paul is a professor at MIT. Ruslan, professor at Peking University. Buwan is a professor at Duke. Roger is at Toronto. Alex is at UIUC. So these are sort of, quite, I think that a third of my students tend to go to academia. Obviously, there's a lot of pull into big tech. So a lot of students do go into, Tesla, Meta, Microsoft, Google DeepMind, NVIDIA. So these are sort of Microsoft Research. These are sort of a lot of students that graduate from CMU. They end up going to the big frontier research labs. And actually, quite a few students go to startups, which is a work at the startups. I think one of the notable example is Ziling Yang. He was a student here at CMU, my student at CMU. He's a founder and CEO of Moonshot AI. If you know about models like Kimi models that are frontier models in China, that's basically he's a co-founder and a founder and CEO of Moonshot AI. And obviously, you have students who went to co-found different startups via robotics, and some students actually do end up going into some of the startup frontiers like Thinking Machines, Anthropic, and others. On that note, thank you very much, and I'm happy to do Q&A.
Wow, Ruslan, that was fantastic. Really appreciate your lab work. That I think a lot of things that you already discussed on that recent podcast, Data Camp, and a lot of information here. You just explore, opening everything on a department-wise. Also, your laboratory work. Really admired. Thank you very much for your time. Ruslan, a couple of questions, and I think we can jump to Q&A session. So let me make this screen so we can with everyone. So Ruslan, so definitely, Ruslan, you witnessed the evolution of AI from early days to deep learning to today's foundation models. And you also, in a podcast, you mentioned currently there's a difference between academia and industry. You have leadership positions in both academia and industry, and you said that currently there's a trend that industry becoming more close, academia is more open. And my question from audience is, what's the big difference in how fundamental research is conducted in these environments? And second follow-up, very quick, how university remain competitive in AI research when industry has access to vastly larger computational resources? Thank you.
Yeah, so very good question. So I think that on your first point, the industrial labs are surely becoming much more closed. We see this with Google DeepMind. I think at Google they used to have Google Brain, which was one very much open research, open environment. A lot of students would go there primarily just because it's like being a postdoc but getting paid like 10x more, right? And so you kind of like openly publish and everything. I think they've shut it down. Same thing happening with Meta. Meta had Facebook Fundamental AI Research Lab Fair. I think they're still publishing, but much less so. And so Part of the reason why is because of competitiveness in the AI space. And part of it, because companies like OpenAI and Anthropic are showing that, good progress in AI and they're not publishing. So both of them are quite close into what they do. And so you have these frontier labs like Google and Meta and others are kind of like trying to follow and kind of shutting down because the idea is that, well, Transformers paper was originally published by Google, even though Transformer was based on a lot of previous work that was done in academia, that was done in different labs. But Google basically at some point said, "Well, we've published a Transformer paper. Now OpenAI is beating us in our own game, essentially." And that they sort of started closing, which is a negative trend in the industry right now. Academia is much more open, and so obviously, as PhD students, we open source everything, we publish everything, and that's why I do want to stay in academia because everything is open. There are some attempts by companies like NVIDIA to build open source systems, but it obviously becomes more expensive, and a lot of models that are coming out of China are actually open source models, and a lot of work is actually a lot of startups and everything is building on top of models that are coming out of China. Model like Kimi, Quen, DeepSeek. So that's a negative trend. I don't know how to fix this, but that's the negative trend. The second question is that how does it academia stays relevant with industry? Yes, that's a big problem. A lot of research, a lot of sort of these interesting behaviors that we see in these systems, especially agentic systems and such, require access to large models, right? And that basically requires large compute, requires GPUs, and that's a problem. Obviously, I can tell you, at CMU we have one of the largest clusters probably in academia. We have 2,000. I think we have like on order of like 1,000 GPUs, and then we have about 200 or like 300 H200s to do research. But at the same time, the problem is that at CMU, we have just the machine learning department, we have 100 PhD students, so 120 PhD students. And so obviously, you have access to maybe 2, 3, 4 GPUs at a time, which is nowhere near enough to actually do large scale experiments. And that creates the problem. And so, yeah, I think that's a problem. But at the same time, I think in academia, we do research in a smaller scale. We do research on like 4B, 8B models, which requires you maybe a couple of GPUs. And a lot of research, still a lot of fundamental research, a lot of good research, I think, is coming out of academia. And so academia will continue to stay relevant primarily as, and obviously there is more collaborations that are happening between academia and industry. And I think it's just that right now everybody's rushing. And so industrial labs are just closing down because they want to catch up. Everybody wants to catch up to OpenAI, to Anthropic and Google. So yeah, but I do think that academia will stay relevant. I see, a lot of because like I think that in the industry, when you look at these frontier labs and you look at the AI, they're not doing really fundamental AI research at the frontier labs. A lot of it is very much engineering work. You'd be surprised that the architectures that people are using are the same architectures that were published in 2017, right? Like with a few different variations, but it's all about the data, the compute, the quality of the data. Can you collect label data? Can you collect, can you scrape the entire internet? OpenAI, Google, Meta, for example, they've been setting up factories of scanning books. You buy all the books, you scan the books, so you can use this data, and so it's a massive sort of infrastructure and data aspect, engineering aspect.
Ruslan, appreciate this point. Yeah, I think it's a very important question to how to be relevant. Yeah, still in this environment. Ruslan, another question. So there's a question from Mainur. She's saying like you have so many students graduated from your lab going to industry, academia. And just to know, like your supervisor, like your studies under Geoffrey Hinton during your early days of deep learning, what was the most valuable lesson that you learned from him and still guides your research today? And looking back at your career, what decision or opportunity had a great impact on your scientific journey?
Yeah, it's a very good question. I think that Jeff was probably one of the best advisors. I was very lucky to kind of be advised by Jeff. Um, I think that the interesting thing that he gave, and obviously like his lab had some of the best researchers. Like somehow he was able to collect strong research. So Ilya Sutskever, the co-founder of OpenAI, was my lab mate, just was sitting next to me. I know him very well. Um, there is quite a few people like Alex Krzyzewski, who founded AlexNet, was there. And so it's in the early days, Navdeep Jayanti, who was a PhD student who built the original Google speech translation system, was there. So it's like he basically, I think Jeff was able to kind of like put the team together at a time. Deep learning wasn't very
Mm,
important kind of like areas because the compute wasn't, the GPUs were just coming up, but it wasn't, the scale. So people were looking at more classical machine learning, more statistical machine learning. Um, but I think that one of the interesting things that Jeff did, he gave us a lot of freedom into kind of like doing interesting research. And I think that's something that I really appreciated because, I was looking at generative models, even they were not working very well at the time, but he gave us the freedom to sort of gave us the advice and the freedom. So I think he just made the whole kind of like my PhD experience been probably one of the best of my lives. I know you have PhD students here, probably sometimes it's tough, it's hard, it's like, it's not an easy task because you obviously, it's somehow maybe for us wasn't it was competitive, but not as competitive because we were working in this kind of like niche of deep learning. And yeah, he just gave us a lot of freedom and he was there all the time. He was actually like one of the things about Jeff is that he was coding himself, he was building his own models. So I think he just created this very nice environment. So people were naturally happy overall
mm.
as PhD students.
Thanks, Ruslan. Yeah, the main point, make your PhDs happy and everyone will be happy. Yeah, and
Yeah,
there's
yeah,
a
I
lot
think
of
so. I think
discoveries.
so. I mean, at CMU, for example, I can tell you at CMU, it's also a great environment, but still feel like at CMU there is a lot more competition than I saw at in Toronto. So
Mm,
to be fair, quite a few students are stressed. Of course, it depends on you because it's just so competitive. And now it's just becoming even more competitive with
mm.
AI. And you look at your peers publishing papers, and your papers get rejected, and that just creates a little bit of
Yeah,
anxiety and everything. So, but yeah.
absolutely. Yeah, Ruslan, totally makes sense. Ruslan, we are a little over time. Do you have another 5 minutes to another
Yeah,
three
of
questions?
course, of course. Yeah, yeah. I
Yeah,
can I can answer any question. I have plenty of time.
yeah, okay. Let's go to then to audience question. Previous one, pre-submitted question. So let's start from Arjol. Arjol for joining from Texas A&M, nuclear engineer, also doing PhD. Please, Arjol, can you unmute yourself and ask a question?
Yes, sure. Thank you very much for your stamina. So basically, I will just give you context. We are applying LLMs for autonomous control of power plants, nuclear power plants. So it's physical AI. This is what you're doing. Long horizon tasks. This is what you're doing. So it was a perfect match for today. Thank you very much. And the problem that we're facing now is that we are obliged to use local LLMs developed within US. So we are using Gemma 431B, the best what we can get. And for long horizon tasks, in our case, it's like after 1, 2 hours, when the context memory and cache is getting filled, we are doing a lot of things like memory optimization and things like that. But your work of multi-agent computer use, like you demonstrated that it works in the web applications. Do you think it would be applicable also in the physical AI?
Yes, I think so. I think it could be applicable in physical AI. One of the things that we see the gains again from the multi-agent system if some tasks can be parallelized. So if it's what we found is that if really your task is that first you have to do A, then you have to do B, then you have to do C, then you get less because it's like very kind of. But if certain things can be parallelized, then we see biggest gains in terms of both the accuracy and compute time. But the multi-agent systems can also be used for test time scaling. So there's something that's called Monte Carlo tree search, which is a way of agentic systems to potentially, you try to solve and then you break, you're trying to solve in the different ways and trying to solve in the different ways. So this exploration is something that can be used with a multi-agent system. So I think definitely it should be applicable in a lot of domains. It really depends on whether you can parallelize and whether there's like, can you explore the same thing in different ways? And for web kind of like tasks or computer use tasks, because you can solve the same problem in many different ways, so you can kind of instantiate multiple systems that try to, solve it in different ways and recover from failures is another thing that we see. So I think it should be doable. Yeah.
Yeah.
Thank you very much.
Thank you, Azrael, for your question. Yeah, I was worried. I was all going to ask about nuclear plants using AI agent. I remember, Ruslan, you said I don't trust to buy a ticket. So I was.
Yes, I think that, I mean, that's true. Like controlling nuclear plants using LLMs, that sounds a little bit scary, but at the same time, if it's like simulation and, I'm sure there's like humans in control making critical decisions and things of that sort. So, yeah, obviously these agentic systems are still weak enough to be fully trusted. But we do see in coding, for example, it gets to the point where it's actually like very robust and reliable. Like, and obviously, like you have guardrails where if the agent is attempting to do something, it will always ask a human, like, do you want me to write this thing or do you want me to do this thing? And so you can kind of, yeah.
Yeah, before going to next question, Ruslan, do you use agents to buy a flight ticket, or not yet?
Not yet.
Okay. Okay. I remember from that podcast. Yeah, you said totally makes sense. Okay, let's jump to
I think that the accuracy of these systems, like the problem is that if the accuracy of these systems is it like, even if it's like 90%, it's not good enough, right? It's like having an assistant who's booking your travel and then like 10% of the time, your assistant books like a completely random travel, right? And you're like, this is not good enough, right? It's just it's not there yet. I think it will get there. I think it's like, of course it's a user interface and everything. It's looking at your patterns. Like sometimes when I go to California, I always take the same flight. I will stay in the same hotel. So like if it knows a lot of personal information, this is where personalization will come in. If it knows my personal information and everything, then yes, it could probably do a good job. But if it doesn't, then it's at this point it's not robust enough. I mean, it could be useful for things that require not safety. So, for example, one interesting example of web agents, there's a company called Utori, which is actually trying to build these agentic systems on the web. And what they found is that people actually want to use those systems to find coupons. Let's say I want to buy something, and the agent says, "Hey, I'm going to go and find you coupons." Great. If it goes, spends 20 minutes and give me coupons, gives me discount, 10%, 15%. Yeah, sure. If it doesn't, it's okay. Maybe it failed. Maybe there is a discount exists out there, but it failed, but that's okay. So these I would call like, not like critical applications, right? So if it's useful, it's useful. If it can't, it can't. So, and it's been very successful, I think that. So
yes, thank you, Ruslan, for sharing this. Yeah, really enjoy it. So next question from Switzerland, please. Mohammed from UTH Zurich has a question. Please, Mohammed, can you unmute yourself, ask your question?
Sure. Thank you a lot, Professor Salakhutdinov, for the talk. It was amazing. So my question would be, you also mentioned this in your earlier speeches. Yesterday, I was also looking up some benchmarks, and we're seeing VLAs coming up, but they are struggling very much with common sense reasoning. Like they can do math Olympiad tasks, but they cannot decide whether a task was accomplished or not based on the images, based on the video data they are fed. And my question is, what are the fundamental bottlenecks there? What are the foundational problems they're facing? What could be the future track to solve them? What is your opinion on this?
Yeah, it's a very good question. I think that existing systems, I mean, primarily because a lot of systems today are not ingesting video data. a lot of systems today actually rely on images. I've seen examples of Google ingesting YouTube data and sort of doing some form of reasoning with video data, but I don't know how good it is. I think some of the fundamental pieces when you kind of try to do common sense reasoning with video data is understanding the 3D space, so understanding kind of physical environment, right? And this is something that's lagging right now. And I still don't know, is it a matter of just scale? If you take all of the video data and try training the model, and then obviously, how do you train from the video data so that you do understand spatial kind of reasoning and understanding action-based reasoning? What's the right loss functions to set up, right? A lot of things that people are doing right now when they ingest the videos is more like question answering. You get the question and try to answer the question. A lot of it also happens through tokenization, where you take the video, you tokenize images, and you just stitch everything together into one big kind of like input, put it in the transformer architecture, and then make a prediction. And a lot of this, so I think there might be some architectural changes that need to be done. Obviously, one key notion of doing some common sense reasoning or understanding is, can you build some form of a world model? Like if I give you a set of tasks and give you like what you need to do, as a human, I can kind of predict what the future might look like, what potential futures might look like. Existing models are still lagging on that. So whether it's a new architectures or more training is still to be seen. VLAs, visual language action models, I think they're getting better and better in terms of how they were before. But again, this comes down to some form of world modeling. Right. So where instead of just giving the text, your output is actually some form of a state that can generate the future frame, for example.
Thank you, Mohammed, for your question. Thank you. I appreciate Ruslan for this very important explanation. Yeah, well, we have last two questions. So before jumping to Nursultan's question, I will ask one general question that everyone is curious about. So Ruslan, another question, like are you hiring new PhD students, or what's the qualification you're looking for?
Yes. I'm always hiring PhD students. One of the things that CMU has this procedure for PhD students where you have to apply to our department, machine learning department. We have multiple departments: computer science, there's machine learning, there is language and technologies institute. So you have to apply. There is a central committee that screens through the applications, and then once they screen and funnel like the top students, those then would go to the faculties, and faculty will kind of like recommend and such. So I would say if you're interested to be at CMU, just the same as at MIT, Stanford, Berkeley, other places, it definitely apply, but you have to go through this initial filtering stage. Just to give you statistics, I think we usually get 1,100 applications, on the order of 1,100 applications, and we accept about 50 students. Maybe a little bit more, maybe 55. Maybe 55, 60 students, and we make offers, and then our yield, what we actually accept, is about 30 students, because out of those 60 students, about 30 students end up going to our competitors like Stanford, MIT, Berkeley.
Yeah, definitely. So thank you, Ruslan, for sharing this. So before heading to last question, so really appreciate, guys, a lot of great questions, but unfortunately due to time limitations, maybe another question we will address next time. So just a quick, before we end the next question, we want to take a group photo with Ruslan for memory. So if you don't mind, please share your camera, show yourself, and just for memories. I think it's very good. And last question, Nursultan, after that, you can ask your question and we will finish the session. Thanks, guys. So 1, 2, 3. Another one. 1, 2, 3. And last one. Here's we have several pages. Okay, thanks for that. So Nursultan, can you address your question and we will finish the session. Thank you.
Thank you very much. Honestly, I am participating very first time, so really appreciate you. So I am a computer science teacher for the last 12 years, and in the last years, with rapidly growing AI, what core computer science and programming principles should we focus to ensure that our students will remain robust and adaptable?
It's a very good question. It's a very good question. What are computer science principles you need to do? So at CMU for our undergrads, right, there are obviously all the fundamental computer science courses like data structures and programming are important. Programming in C and Python, I think those two are very important. Maybe I'm a little bit biased towards AI, but in AI, a lot of work, a lot of things are happening in combination of C++ and Python, right? All the languages like PyTorch, JAX, all the environments, a lot of them are based on the Python. But the knowledge of C++ is also very important because a lot of core backbones are built on C++. And I think that if you're teaching computer science to students, I mean, those are very important. But I think that also, at least in AI, strong foundations of machine learning, strong foundations of deep learning, some of the recent sort of language models, architectures, and sort of also combination of computer science and statistics. A lot of times what we actually do is we do statistical optimization. A lot of times we're optimizing loss functions. And so optimization becomes also fairly critical. And from statistics, it's sort of understanding like expectations and all the core stats kind of, or what we call statistical machine learning becomes very important. So at places like big tech, a lot of times they would really test your knowledge, fundamental knowledge of computer science, languages, how strong of a programmer you are, machine learning fundamentals, as well as more recently the large language models, the architectures and everything. And a lot of it is, look, transformer architectures, for example, it's mathematically not a very sophisticated object, but once you start coding it up and once you start making it faster, and the memory aspect of it and KV caching, all of these pieces become super important. And at CMU, at CMU, we're trying to teach some of these concepts, and a lot of times getting students to program some of these key components themselves is actually extremely useful. So yeah. Nobody writes, for example, nobody writes backpropagation code nowadays, right? Because in PyTorch you can just it's all. But I think it's useful for students to just derive and chain rule and write the backprop code and write the attention mechanism code yourself once, and then that gives you a far stronger understanding of what goes behind.
Yep. Yeah. Thank you very much.
Thank you, Ranjan. I have one more personal question, if you let, of course. If we are out of time, okay, no problem.
We're a little out of time. Maybe we will forward. So Ruslan, thank you very much for dedicating your time, joining from US this morning. And with this, a lot of students, PhDs, postdocs, and some professors also joined today. And everyone, thank you for joining your weekend time. And we really appreciate our association, always straightforward to bring this great minds that come from our region, and in order to create this ecosystem between us and guide our young scientists. So thank you very much for joining, Ruslan. I appreciate your time. We will keep in touch. Thank you, everyone. Have a good weekend.
Thank you. Thank you. Bye.
Thank you.
Bye.
Thank you. Bye-bye.
Bye-bye.
Thank you so much. Bye-bye.
Bye-bye.
So I have some questions for founder.